Have you ever just stopped and wondered how the apps on your phone or the websites you use every single day actually work? It really does seem like magic, but it all comes down to a fascinating process of translation. Today, we're going to pull back that curtain and see exactly how a simple idea in a person's head gets turned into a powerful program on a computer. It all comes down to this one single question. You type a command, right? And somehow the machine just understands and does what you want. But how? What's really happening in that gap between your keyboard and the computer's brain, the processor? Well, that's exactly what we're going to break down. Okay, this right here really shows you the massive gap we're talking about. Look on the left. You see these friendly, colorful blocks. It's visual, it's intuitive, something a person can look at and just get. But then look on the right. That is what the computer actually understands. It's just a long stream of ones and zeros. That's binary. It's like we're speaking two completely different languages.
And that leads us directly into our first big challenge. Getting our human ideas into a form the computer can act on means we have to figure out a way to cross this huge language barrier. Honestly, it's the core problem that all of programming has been trying to solve for decades.
Here's the thing. We think in abstract ideas, in words, in logic. A computer, though, at its very core, only understands electrical signals that are either on or off. That's it. We represent that state with ones and zeros, which is binary. And the language built from all that binary is called machine code. It is the only thing a computer's processor can execute directly. So, how in the world do we bridge this massive communication gap? Well, thankfully, we don't have to learn to speak in ones and zeros. Instead, programmers have come up with a really clever solution, creating different layers or tiers of languages to act as a middle ground. Let's take a look. First up, we have high-level languages. Think of things like Python or Java. They're called high-level because they're way up high, far away from the gritty details of the machine's hardware. They use words that look a lot like English and logic that feels familiar. This lets programmers focus on the actual problem they're trying to solve, not on, say, managing the computer's memory. And then, on the complete other end of the spectrum, you have low-level languages. These are way down low, much, much closer to the computer's hardware. The most fundamental, of course, is machine code itself, the raw ones and zeros. Just one tiny step above that is something called assembly language, which uses simple words as a sort of shorthand for machine instructions. But still, it is incredibly difficult for a human to work with. And this table really lays out the trade-offs perfectly. High-level languages, way easier and faster for us to write, but they can be a bit slower and not as efficient when they run. Low-level languages, on the other hand, give a programmer incredible power and speed because they're controlling the hardware directly. But that power comes at a huge cost. It's so much harder and takes way longer to write. That's why I say a super high-performance video game might use a lower-level language, but a simple website would almost always use a high-level one. Okay, so we've got our human-friendly high-level code, and we've got the machine code the computer needs, but we still need something to connect them, and that's where our translators come in. These are the real unsung heroes of programming. They are special programs that do all the hard work of converting one language into another. The whole process really simplifies down to these three steps. First, a programmer writes the code. Second, a translator program converts it. And third, the computer runs the final machine code. It's a clean, powerful workflow that literally makes all the software we use today possible. Now, our first type of translator is the compiler. I want you to think of a compiler like a really meticulous book translator. It reads your entire program from the first line to the very last and translates it all at once into a complete, separate file of machine code. This is why the apps on your phone are so fast. They've already been pre-translated or compiled into efficient code that's ready to run in a flash. The second type is the interpreter. An interpreter is more like a live, simultaneous translator you'd see at a big conference. It reads one single line of your code, translates just that line, tells the computer to run it, and then it moves on to the next line. It translates and runs as it goes, which gives you really immediate feedback. And just to cover all our bases, there's one more called the assembler. Remember that really low-level assembly language we mentioned a minute ago? Well, this is its dedicated translator. It has one very specific job: take those simple command words and turn them into the final ones and zeros of machine code. So when would you use one over the other? Well, the interpreter is your best friend during development.
because it runs your code line by line. It's so much easier and quicker to test things and find mistakes. The compiler, on the other hand, that's for the finished product. The compiled program is fast, it's efficient, and it doesn't even need the translator to run anymore. That makes it perfect for shipping out to users.
All right, so we've got these powerful translation processes, but where does a programmer actually, do all this? Where do they bring all these pieces together to write and translate the code? They don't just use a simple text document, no, they work inside a powerful digital workshop. And this workshop is called an Integrated Development Environment, or an IDE for short. An IDE is basically a massive application that bundles all the essential tools a programmer needs into one single place. You can think of it as the command center for building software. So what's inside this toolkit? Well, you get a specialized code editor, you get a built-in translator, either a compiler or an interpreter, and you get these incredibly helpful features like error checking that spots typos and auto-completion that suggests code for you as you type. But maybe the most powerful tool of all is the debugger. Let's look at the heart of the IDE, the code editor. As you can see here, this is not just a blank page. It has cool features like syntax highlighting, which color codes your text to make it way easier to read and spot mistakes. This is where a programmer's ideas first start to take shape as actual, high-level code. And here it is, the programmer's secret weapon, the debugger. When a program isn't working right, and trust me, that happens a lot, a programmer uses the debugger to hunt for the errors, or as they call them, bugs. It lets them literally pause the program in midair, step through it one line at a time, and inspect everything to see exactly where things went wrong. It's like having a slow-motion replay for your code. It's a lifesaver. Okay, so let's zoom out and take one last look at this whole journey, putting all of the pieces together. What this all adds up to is just this brilliant tower of abstraction. The entire system, from the high-level languages to the translators to the IDEs, it's all designed to hide the complexity of the layer below it. This is what empowers us as humans to translate big creative ideas into real action without ever needing to think like a machine. And that leaves us with one final thought. We've spent decades building these amazing tools just to make computers understand us better. So as technology like AI continues to advance, what do you think the next layer of abstraction is going to look like? What's the next big step in making the conversation between humans and machines even more seamless? Something to think about. Thanks for tuning in.